Okay, so let's start with the second day of our workshop. So we will start with the talk of Pablo Barcelo, who will talk about query languages for machine learning models. So thank you.
Thank you. Okay, so I'll be talking about query languages for machine learning models, and I'll put special emphasis on explainability tasks, how to express explainability tasks in these languages. But since there are several people here who work on verification, one of the reasons why I was so interested in coming here was to try to interact with this community and see how these query languages can be of help to verification tasks as well. Yeah. So if we can go in this direction or discuss in this direction, yeah, please stop me at any point and we can talk about it. So there are current requirements on machine learning. I mean, this community knows it very well. Machine learning models need to be explained and verified. Yeah. And when you think about explainability, there is actually a myriad of different queries and scores proposed for explaining neural networks. For instance, minimum sufficient reasons, I'll be talking about them later, minimum change required, or some game theoretical notions such as, sorry, I have to, okay. Game theoretical notions that try to measure the importance of a feature, the contribution of a feature to the output of a model. These are SHAP score, BANSAP scores, and so on. But also verification of neural networks poses diverse challenges to them. One of them is robustness. Another one is fairness, monotonicity, correctness, and so on. So we have a challenge here, right? The challenge is that we want to deal with different queries, with different scores, with different properties, and we don't want to be developing systems one by one, right? We don't want to be developing systems for this query, and so on. And this is a very known challenge for the theoretical computer science community. And the way this challenge has been handled in several areas is by developing declarative query languages. Query languages in which you express what you want to retrieve from the model, but not how to do it explicitly. And we believe that declarative query languages for neural networks can be helpful for several reasons. First, they allow you more flexibility at the moment of writing queries. Yeah. So we know that for explainability, there is no silver bullet that tackles all explainability problems, but there are different queries, right? And this allows you to develop or express the queries that you really need for your application, providing a clear syntax and semantics for such queries. Making tools more accessible to practitioners. Since the query languages are declarative, this can help in the adoption of these techniques in broader communities. And finally, something that has happened, for instance, in verification or in databases is opening a path for optimization of queries. Yeah? So let me start with a model agnostic approach for explaining Boolean machine learning models with query language. By model agnostic, I mean that we're not going to look into the internals of the models, but we're going to look into their input-output behavior. So what is the explainability problem? So we have a Boolean model that is a Boolean function, yes, and a Boolean input that is a list of features in 0 and 1. And the question, the overall question, is how can we explain the output of this Boolean function on E, right? What is the reason that this model is outputting this value on E? So a bit of notation here. We assume the set of features of the Boolean model to be capital X. We have n features x1 to x of n. We have an input function, an input to the model that is given as an assignment from x to 0 and 1. And we're going to write m of E for the output of the model on this input. So as I said, several several different queries have been studied in this context. One of them is counterfactual explanation. So if I have a Boolean model M and I have a set of features X and an input, yeah, we call a subset of the features Y a counterfactual explanation for M and E if whenever I flip the values in the features that are contained in Y, the output of the model also flips. That's a counterfactual explanation. Yeah. So it's an explanation of what could have happened if I had flipped the values of these features. We want counterfactual explanations that have some sense, some guarantees. And typically we look for those counterfactual explanations that are minimum in terms of size. The smaller the size of the counterfactual explanation, the better. But people have also studied a different notion that is called a sufficient reason. A sufficient reason for M and E is a subset, again, of the features, a subset Y of the features, such that every input that coincides with E in those features for Y has the same output with respect to the model. That is, the model is invariant with respect to the interpretation of the features that are outside Y. Yes? With respect to this particular input E. Yeah? Every input that coincides with E over the features in Y has exactly the same output. Yeah? So that's a sufficient reason for this, for the output of the model with respect to this input. And again, we look for sufficient reasons that give us some guarantee. The best we can find is a minimum sufficient reason, that is a sufficient reason of the smallest possible size. And when that is difficult to compute, we may want to compute one that is minimal. That is, there is no sufficient reason set that is properly contained in Y. Yeah? So here there is a simple example. If we have the model that consists of the disjunction of X1 and X2, and we have as input the assignment that assigns value 1 to each one of the features, then the minimal counterfactual explanation for this model and input is both features, right? Because we need to flip both features in order to change the output of the model. While the minimum sufficient reasons are X1 and X2, because every input that has a 1 on any of them will output a 1. Yeah. So how to define query languages that are capable of expressing this kind of queries? So first of all, we have to define a logical structure that represents Boolean models. And we're going to do it in the following way. We're going to represent the Boolean model M over a set X of features with N features as the following logical structure, A sub M. So the domain of the model will contain all tuples of size N that contain 0, 1, and an undefined value bottom. And we will have two relations on top of this. We will have a binary relation that we call subsumption and a unary relation that talks about the model. Yeah. So bottom represents an undefined value. The domain of the structure represents all partial inputs, right? All inputs in which some of the values, but not necessarily all of them, are assigned 0 or 1. The binary predicate subsumption contains pairs E and E prime of partial inputs such that E prime is more complete than E. What it means? It means that some of the undefined values here in E have been replaced by zeros and ones in E prime. Yeah. So for instance, 1 bottom bottom is less complete than 1 0 bottom because we have replaced this undefined value by 0. Yes, so that's a subsumption relation. And the unity predicate positive is the one that talks about positive inputs of the model, right? So these are the sets of complete inputs, yeah, not partial inputs, complete inputs, for which the output of the model is 1.
Excuse me, maybe just clarification. So model is not known for you, right?
The model is not given to you. The model is given, it can be given as a decision tree, but this logical structure is not given to you because it's exponentially sized on the, but we use it implicitly as a way to reason about the underlying, so the logic will be defined over this structure, but this structure is not given to you.
So you also don't know what is a set of poles, right? You know that it exists? Or
you know, yeah, you don't need to compute it in advance.
Yeah, okay,
you know it exists. Now you'll have to reason about it somehow. Right?
Thank you.
So we define the logic first order interpretability logic, FOIL, which exists in a different community, unfortunately, as first order logic over structures of the form that I showed before. It's just first order logic over these structures that represent Boolean functions. So let me show you some examples. The domain of the model is the set of partial instances, right? But I can define full instances, for instance. A full instance X is one such that every Y that is more complete than X is precisely X. I can define the binary predicate full completion as follows. Y is a full completion of X if Y is more complete than X and Y is full. Yeah. I can define the pairs of same class full instances as follows. I can say that X is full, Y is full, and one is positive if and only if the other one is positive. Yeah, so they are in the same class. Now I can start defining things about sufficient reasons. So for instance, when X is a sufficient reason of Y? Well, first of all, Y has to be full. X has to be X has to be subsumed by Y, right? So X is obtained by undefining some of the features in Y. And every full completion set of X is in the same class as Y. That's a sufficient reason, yeah? And now with the logic, we can define, for instance, minimal sufficient reasons. What are minimal sufficient reasons? Those that do not properly contain another sufficient reason. So minimal sufficient reason is a sufficient reason such that for every set that is also a sufficient reason of Y, and it is contained in X, then it is equal to X. Yes, that's a minimal sufficient reason. Now, this logic is very simple and very clean, but it has two issues. The first issue is that it has limited expressive power. It cannot express all the things that we want. Yeah, and I'll show a result that captures this idea. And the second issue is complexity. The evaluation complexity of this logic is prohibitively expensive even over very simple models. Yeah? And I'll also show you a result that captures this. So the first issue is expressiveness. The minimum sufficient reason, that is the one of smallest possible size, is not expressible in this logic even over the class of decision trees. We cannot express it, right? Intuitively, FOIL is nothing else than first order logic, and thus it doesn't have the ability to compare the cardinalities of sets of features. Yeah. And in terms of complexity, what we can show is that the data complexity, that is for fixed queries, the data complexity of FOIL is hard for every level of the polynomial hierarchy, even over the class of decision trees. So even over very simple models, computing the the values of these formulas, even if the formulas are fixed, can be extremely costly. So we have conflicting requirements here. We need to design a logic that is at the same time expressive enough to be able to capture notions of explainability often found in practice and can be evaluated efficiently over decision trees. Yes? So what efficient means in this case? Our notion of efficiency will be formulas that can be evaluated as Boolean combinations of MP languages. Why is that the case? First of all, it's unavoidable because if we want to compute minimum sufficient reason over decision trees, we know that this is a co-MP complete problem. Yeah? So if we aim for, say, tractability, we would be leaving some important notions behind. And on the positive side, Boolean combinations of MP language allows us to use SAT solvers technology to evaluate formulas in the language. And that's precisely what we do in the practical part of the paper, which I will not be presenting here. So let me talk about a language that fulfills these two requirements. And in this case, it will be a declarative language for explaining decision trees. So the first thing about this logic that we call decision tree foil is that it's no longer model agnostic. It talks about decision trees. Later, we will go back to the idea of model agnostic languages, but this one is not model agnostic. No? And this language is composed of 3 layers. We have a layer of atomic formulas that can only compare syntactic properties of partial inputs. That is, they do not talk about the model itself. They only talk about syntactic properties and can be evaluated in polynomial time. Guarded formulas that allow quantification over partial inputs that represent nodes and positive leaves of the decision tree. That is, they will not be arbitrary partial inputs. They will be partial inputs that represent some particular things in the decision tree, and there will be polynomially many of them. And this second layer can also be evaluated in polynomial time. And finally, the DT foil formulas themselves, which are Boolean combinations of quantified guarded formulas and can be evaluated as Boolean combinations of MP languages. So what are atomic formulas? Atomic formulas will be formulas in first-order logic over the following syntactic relations: the subsumption relation, that is very important for us, and a binary relation that allows us to compare cardinalities of sets of features. So we will have this notion that this binary relation that contains all pairs of partial instances E and E prime, such that the number of undefined features in E is no larger than the number of undefined features in E prime. This is a simple syntactic property that allows us to compare cardinalities of sets of features. On the other hand, what are guarded formulas? Guarded formulas are recursively defined as follows. First of all atomic formulas are guarded. Guarded formulas are closed under Boolean combinations. And finally, if phi is a guarded formula, then the two following formulas are also guarded. We can say that there exists a partial input that represents a node of the decision tree, or there exists a partial input that represents a positive leaf of the decision tree, such that something holds. Yeah. So node of X holds for those partial instances that corresponds to nodes of the decision tree. So I take my decision tree, I take a node, I look at all defined components from the root to this node, and this defines a partial input, right? Yes. And the same for a positive leaf. I take a positive leaf of the decision tree, I take all defined features from the root to this positive leaf, and this also defines a partial input. The important thing is that there are only polynomially many nodes in the decision tree and polynomially many positive leaves. So here, I'm quantifying over a polynomially sized set. Yeah? And finally, we define DT foil formulas as follows. Guarded formulas are DT foil formulas. DT foil formulas are closed under Boolean combinations. And if phi is a guarded formula, then I can existentially quantify over it and construct another DT foil formula. So here, the quantification is unrestricted. And this gives us the power of an MP language. Yeah. So with respect to expressiveness, we can show that DT foil is a good language in terms of expressiveness. So we can express many things that appear in practice related to explainability in this language. So DT foil is capable of expressing several useful explainability properties often found in practice. Let me give you two examples. Let us think of a minimum sufficient reason. So a minimum sufficient reason is a sufficient reason of the smallest possible size. When you express this in foil, this involves a quantified alternation. You have to say that something is a sufficient reason and there is no one of smaller size. So there is a quantified alternation. But our language doesn't allow for quantified alternations. So we have to do this in a more clever way. Yeah? How do we do it? First of all, we define a formula that tells us when partial inputs x and y are consistent. What it means they're consistent, then they have the same values in those defined features. How do we say they're consistent? Well, there has to be an upper bound for both of them. That's the only way in which they can be consistent. We can define when something is a leaf. Something is a leaf if it is a node and there is no node that strictly subsumes x. We can define when all completions of a node are positive. We have to say that every y that is a leaf and is consistent with x is a positive leaf. Yeah, that's how you do it in a decision tree. So now we can express sufficient reason without needing to have any quantification here, right? So we can do it in the following way. We can say that x is containing y is full. If y is positive, then all completions of x are positive, and if y is negative, then all completions of y are negative. Yeah. So now we can use our cardinality, our relation symbol for cardinality comparison to express that something is a sufficient reason. We say that x is a sufficient reason, sorry, it's a minimum sufficient reason. So we say that x is a sufficient reason of y, and every set that is a sufficient reason of y has at least as many undefined features as x. Yeah? But we can also express other notions like minimal counterfaction. So I'll not get into details because I'll be running a bit out of time, but the logic allows you to express that something is a minimal counterfactual explanation. And basically what we have to do is to define the Hamming distance between these different full instances that can be done in the logic as well. Now, the good thing, the logic is expressive enough and also can be evaluated with a constant number of calls to an NP oracle, yeah, over decision trees. Yeah. Now, decision trees are important, but of course, they are far from being like the most important models we have this far, right? So the question that we raised to ourselves was, can we use similar ideas to define a model agnostic language? This language was not model agnostic, that can be evaluated efficiently over a well-behaved class of models. Yeah? And this is the question that I'll try to answer next. So model agnostic languages for explaining more general models. And the first thing that I'll try to do is to define what are these more general models. These general models are based on Boolean circuits. So let me quickly remind you what is a Boolean circuit. In our case, a Boolean circuit over a set X of variables is a directed acyclic graph C such that each node without incoming edges, the input is labeled with a variable or a constant. Each other node is labeled with a Boolean gate. And there is a single node without outgoing edges that we call the output. Now, for an entity E, an input, an assignment of the variables, we're going to say that C of E is 1 if and only if E is accepted by this Boolean circuit in the standard way. So Boolean circuits, even checking whether there exists a positive output, a positive input for the model is an NP-complete problem, right? So people have analyzed when these Boolean circuits, which restrictions on Boolean circuits lead to efficient procedures. And they have come out with this very general class that is called deterministic and decomposable Boolean circuits. So what are them?
Excuse me.
Yeah.
Again, have a clarifying question.
Yes.
So model previously you consider mostly decision trees, right? Previously.
Previously, yes.
Yes.
So the negative results apply to decision trees, and the positive results that we have seen so far only apply to decision trees.
Okay.
Yes.
And now you're considering circuits.
Now I'm considering circuits because I'm trying to extend the positive results to circuits. Mm-hmm. These circuits embed decision trees.
For me, I kind of don't see the difference because I think they can all be encoded as formulas. So that's what I'm missing here.
Decision trees can be encoded as formulas, of course, yes.
Yeah.
Yes, but they are, what we want is like formulas that are well behaved for this language, right? So that classes of formulas or classes of circuits for which the evaluation problem for this language is still solvable as a Boolean combination of NP languages. So if you take arbitrary formulas and you take this language, it will be very expensive. Yeah, so we need to consider well-behaved classes of formulas or circuits. And this is precisely what we're trying to do here, yes. So what are deterministic and decomposable Boolean circuits? Well, if I have a gate G in the circuit, I'm going to define two things. C sub G is the circuit induced by the gates G prime in C that are below G, yeah, in the subtree induced by G. And bar of G will be the variables that appear in this circuit induced by G. So a Boolean circuit over a set X of variables is deterministic if every time that I have an OR gate, there is no assignment that satisfies the left child and the right child. Yes, this is a semantic property. It's hard to verify, but it doesn't matter. We are going to work with circuits that satisfy this. Yeah. And decomposability means that every time that you have an AND gate, the variables that come from here and the variables that come from here are disjoint. So basically, deterministic and decomposable Boolean circuits are designed to be able to count the number of satisfying assignments in polynomial time. Why? Because if you have an OR gate, you know that there will be no satisfying assignment from here and here. So you just have to sum the satisfying assignments. Yeah. And AND gates do not share variables from one side and the other. So the number of satisfying assignments here will be the product of the satisfying assignments from here and here. Yeah. So this is an example of a deterministic and decomposable Boolean circuit. I have an AND gate. The variables that come from the left-hand side are disjoint from the ones that come from the right-hand side. And I have an OR gate here. But the good thing is that Y that comes from the left is negated when it comes from the right. Right? So there will be no satisfying assignment that satisfies this path and this path at the same time. Yeah? So it's an unambiguous disjunctive normal formula here you have. So the deterministic and decomposable Boolean circuits are quite powerful in the sense that they can embed several of the models that we are interested in. First of all, decision trees, OBDDs, ordered binary decision diagrams, something that is familiar to people who work in verification. Free binary decision diagrams, yeah? All of this can be embedded in polynomial time as the deterministic and decomposable Boolean circuits. So if we can prove positive results for this class of circuits, we will be obtaining positive results for all of these classes at the same time, yeah? So we have designed a logic that is model agnostic and can be evaluated in polynomial time over deterministic and decomposable Boolean circuits. So the logic is again composed of 3 layers. The atomic formulas are exactly as before. The guarded formulas are slightly different, but very simple to define. And the F-foil formulas are exactly as before. Yeah? So the atomic formulas are the subsumption relation, first order formulas over the subsumption relation, and over the relation that allows us to count, to compare the number of undefined features. Now, for guarded formulas, we will use an important class of first order formulas. So we are going to say that X is completely undefined if all the features of X are undefined, all of them. This is just bottom, 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 right? And this is definable in the logic. And then we're going to say that X, a partial input, is a feature if there exists exactly one value that is defined. So this is a feature. It's a partial input that represents a feature. Yeah? Now, guarded formulas are defined as follows. Atomic formulas are guarded formulas. We will have guarded formulas for all pos and all neg. That is, all completions of X are positive, all completions of X are negative. And then we will have this kind of existential quantification. There exists an X such that X is a feature and phi satisfies phi. So there exists a linear number of features, right? So this quantification is over a linearly sized set. And finally, F-foil formulas are Boolean combinations of existentially quantified guarded formulas. No? I'll not get into details here in terms of expressive power, but all of the things that we could express in the previous logic can still be expressed in F-foil, yeah? And sometimes even in a simpler way. So F-foil is capable of expressing several useful explainability problems often found in practice. And in terms of the complexity, this is quite positive because the problem of evaluating a fixed formula from this logic over the deterministic and the decomposable Boolean circuits can be solved by a constant number of calls to an NP oracle. So we are able to use such solvers technology as long as the Boolean circuits are not so large. All right. So far, I have been talking about Boolean models, right? And this is important in practice, of course, but it is, of course, natural to ask, what if you have real valued models? Yeah? And there has been a recent proposal on this that I think it's worth explaining. What is this? What is the setting? In this case, a machine learning model is a function that takes an m tuple of reals and outputs another real. Yeah? And the proposal was to consider first order logic over the reals with the function that represents the model. So it's first order over the structure of the reals with plus, times, 0 and 1 with access to the emery function f. Yeah? So here is an example. We may want to check whether the, say, neural network f is robust around a vector x over the reals. And here epsilon and delta are user-defined constants. So we will say, for every y, if the distance between x and y is at most epsilon, and the distance is something you can express in this logic, yeah, in first order over the reals, then the difference between the output of x and the output of y is at most delta. Yes. The following formula looks, for instance, for the closest counterfactual to the vector x. We're going to say the output of our vector x is not good enough, it's at most 0.8. So we are going to look for a y such that the output of f on y is larger than 0.8. And every set for which the output of the model is larger than 0.8 is closer to, is farther away from x than y. So y is the closest counterfactual. No? So this can also be expressed in the logic. So the observation made by the authors of this paper is that as long as f is expressible in first order over this structure, then the evaluation of the logic is decidable. And why is that the case? Because we have this very strong result by Tarski that talks about the decidability of the first order theory of the reals. Yeah? And are there interesting examples of when f is expressible in first order over this structure? Yes. This property is true, for instance, when f is a feed-forward neural network with ReLU activation functions. This can be expressed in first order over the reals. And in fact, you can prove something stronger. If I give you a fixed first order formula over this vocabulary, then the problem of evaluating this formula over a feed-forward neural network can be solved in polynomial time. And the main reason for this is that this structure, the reals, has a quantifier elimination. So we can bring back the formula is fixed, so we don't pay the cost of finding an equivalent quantifier-free formula, right? So we decompose it into a quantifier-free formula, and then we evaluate the quantifier-free formula over the structure. Yeah, that's a basic idea. This paper has been published in ICDT 2025, I guess, but it was proposed in 2024. Also contain a logic for querying neural networks that is not model agnostic, yeah, that it talks about the internals, the weights of the neural network. And the expressive power of this logic is then compared against the black box logic that I showed you before. So let me finalize with some open problems here. First of all, how to extend these results to allow for counting and aggregation in the logic. Yeah, our logic doesn't contain counting beyond this very simple binary relation symbol that allows to compare cardinalities of sets of features. And this is important because our logic can still not express scores such as SHAP or Banshaf, but it might be able to express them once you have counting on it. What is the cost of evaluating our logic over neural networks? We don't know this. And if this is too expensive, which is probably the case, can we find a reasonable logic that can be evaluated with a constant number of calls to an NP record? And finally, can we define general purpose query languages for machine learning models that subsume the needs expressed by both explainability and verification? Yeah. So the examples that I showed for Boolean models were based mostly on explainability, while the ones I showed for the real valued logic were mostly based on verification, right? Can we bring them together in a unifying logic and try to understand the complexity of these things? Well, thank you.
Let's thank the speaker. Are there questions?
Are any of your results on the first part, that is on the Boolean circuit part?
Yes.
The DD Boolean circuit, are they applicable to Booleanized neural networks?
Yes.
Have you tried using it on any of
Yes.
those benchmarks?
I don't know about the complexity. Yes, but yeah, no, I haven't tried. No, we have implemented SAT solvers over the deterministic and the composable variant circuits. That's the farthest we have gone. But I think it would be very interesting to try them over neural networks. That's something that we have to do. Yes.
Ask question about, you said that you're analyzing networks which has ReLU function. What about those who have as activation like sigmoid and friends? So I mean, I know, I was just thinking about Tarski. Does it also allow trigonometric function or not?
Oof, that's
Yeah, like I was.
Yeah.
No, okay.
But the theory of the reals with the exponential function that you need for sigmoid.
Yeah.
I don't want to say something that I don't remember well, but my guess is that this is decidable.
Yeah.
And this seems to be a very strong result in model theory, you know? Yeah, is it?
I don't know, because when moment you said like, okay, yeah, like, and then you mentioned Tarski, I'm like, wait, what about the others? And then, you know, like this was somehow all the time under my background.
There are some powerful extensions of Tarski's result.
Exactly, that's what I was thinking, like, will someone else say like, yeah, of course, or no, of course.
Yeah, but I don't want to say something for posterity that it's
similar here. I'm also thinking like, is it or is it not?
Conjecture thing. So this is implied by the general. This is
educate people on the call.
Sorry. Yeah. This is implied by the general conjecture. So I think if you would solve these things, then you.
Which exactly the trigonometric function?
Yeah, with the exponentials, right? So I mean, this has been open for a long time, I believe.
Yeah.
Okay. So are there more questions? If not, in the interest of time, let's kind of thank speaker once again. And next speaker is here. So.